Hello students, now in previous video we have seen some examples. Now here also let me take some 2-3 examples are left, so let us take them first and later on we will go for our next topic. So now as in previous video we have shown that the GCD of A, B and C is same as the GCD of A, B with C. Similar thing we can show that GCD of A with GCD of BC. Also GCD of AC and B. All these things are what? Equal. Already we have written this as a note. Now the same thing let me prove for n numbers. Now this is for 3 numbers. So let us prove for n numbers. Means what I want to show GCD of A1, A2 and so on up to what? AN is same as GCD of A1, A2 and so on up to AN. First of all we will determine this GCD and then the GCD of the GCD with AN. These things are what? Equal. So let us prove this part first as an example. So our example is that prove that the GCD of A1, A2 and so on up to what? AN is same as the GCD of A1, A2 and so on up to AN minus 1 and AN. So proof of this one. Now suppose let us assume this GCD of this one is some number. Suppose the GCD of A1, A2 and so on up to AN is suppose D1. If this is the case, then you know this D1 divides A1, D1 divides A2 and so on up to D1 divides what? AN. Now GCD divides to each and every number there. Fine. So as this is true, so this says A1 is equal to what? D1 into K1. A2 is equal to what? D1 into K2 by property of divisibility. AN minus 1 equal to what? D1 Kn minus 1 and AN is what? D1 Kn. For some K1, K2 and so on up to what? Kn, these are what? Integers. These are integers. Fine. Now also let us assume the GCD of this A1, A2 so on up to AN is suppose G. Also assume GCD of A1, A2 so on up to AN minus 1 is what? G. So if this is, therefore again G divides A1, G divides A2 and so on up to what? G divides AN. Here one number is less, obviously the GCD is different. Here these are n numbers, here these are n minus 1 numbers. Fine. So that GCD again divides to each one. So now here as this divides each one, then again by the definition of divisibility we get A1 is equal to what? A1 is equal to G K1. A2 is equal to what? G K2 and so on up to AN minus 1 is equal to what? G Kn minus 1, or let me say dash G K1 dash, G K2 dash and so on up to G Kn minus 1 dash. For some K1 dash, K2 dash and so on up to what? Kn minus 1 dash. These are what? Integers. Fine. Now let me take this GCD is what? G. That G with AN, that GCD. Now again let the GCD of G and AN is what? Suppose D2. So now GCD of G and AN I had assumed D2 and GCD of A1, A2, what? D1. These are also n numbers, but first of all the GCD of these n minus 1 numbers we have assumed G. So these two things we have to show equal, means we have to show D1 equal to what? D2. Our claim is that D1 is equal to D2. Fine. Now if this is, then again by the definition of GCD, D2 divides G and D2 divides AN also. Fine. If D2 divides G and AN, this gives again by definition of divisibility, G is equal to D2K and AN is equal to D2KN dash, suppose. For what? K and Kn dash are what? Integers. For K and Kn dash are integers. So if this is the case, G is what? D2K. Let me substitute this value of G here in A1, A2, so on up to AN minus 1. What does that give? Therefore, I get A1 is equal to what? D2K K1 dash. A2 is equal to what? D2K K2 dash, and so on up to AN minus 1 is equal to what? D2K Kn minus 1 dash. Fine. Now these things we are getting here, the values of A1, A2, AN minus 1 in terms of D2 and AN also in terms of D2. Now our claim, already I taught you, our claim to show, claim is what? D1 equal to what? D2. Then these two things are equal. Fine. Now as our assumption, this part, as our assumption, this GCD is what? D1, this GCD was G, this GCD was D2. Now let me take this G first. So A1, A2 and so on up to what? AN minus 1 is equal to what? G. So if this GCD is G, then by existence or by linear combination theorem, therefore by existence theorem, we get, by existence theorem, what does we get? We get there are n integers, the linear combination of the product of n integers with these n integers is equal to what? G. So A1 x1 n minus 1 integers, sorry, A2 x2 plus so on up to what? AN minus 1 xn minus 1, AN minus 1 xn minus 1 is equal to what? G. For some x1, x2, so on up to what? Xn minus 1 belongs to what? Z. This is the case. Now here let us substitute the value of A1 up to AN minus 1. So now let me substitute the value of A1 and AN minus 1 as this. A1 is equal to D1K, D1 K1, D1 K2 and so on up to Dn Kn minus 1 respectively. So now this implies, what does this give? This is D1 K1 x1 plus D1 K2, sorry, D1 K2 x2 plus so on up to what? D1 K n minus 1 xn minus 1. That is equal to what? G. Now I can take D1 common and wait, I don't want that thing, okay, leave it. I want expression of G in terms of D1. Now why does we need it? We will see it further. When I use the existence theorem here, I need the value of G here. That's why I found the value of G in terms of D1. Now I have to show D1 equal to D2. So to show D1 equal to D2, I simply want to show D1 divides D2 and D2 divides D1. So if I got D2 equal to what? Gx plus An. Gx plus An y. Then that g will be substituted this one. So we can easily show that d1 divides d2. For that purpose, I had obtained the value of g in terms of d1. That's why I substituted here a1, a2, an minus 1 in terms of what? d1. Now call this as equation number 1. Suppose we will use this. Fine. Now here I can say also what? The GCD of g and an is what? d2. I want to use this. Fine. Now which theorem we have to use? Again by existence theorem or linear combination theorem. Existence theorem. By existence theorem, what does we get? We get gx plus any is equal to what? d2. Gx plus any is equal to d2. For some xy belongs to what? Set of integer. Now here I want to substitute the value of g. So if I substitute g here, what does I get? I get this gives d1 k1 x1 into x. X will be multiple to each, or let me write this, plus d1 k2 x2 plus so on up to d1 kn minus 1 xn minus 1 into what? X plus an minus 1 is what? This. Sorry, an is this. An is what? d1 kn. So let me write d1 kn into y. d1 kn into y, and that is equal to what? d2. That is equal to d2. Now let us open this bracket. What does we get? Or without opening the bracket, this x will be multiple to each one. Fine. And d1 is here in each term. Here also d1 in each term. I can take d1 common from left hand side. So what does it gives? d1 into k1 x1 x plus k2 x2 x plus so on up to kn minus 1 xn minus 1 into x plus this kny, that is equal to what? d2. So this gives d1 divides d2. d1 is some multiple of d2 is some multiple of d1. This is an integer. All these are what? Integers. So this is also an integer. So I may write d1 k dash is equal to d2, and that gives where k dash is equal to what? k1 x1 x plus k2 x2 x plus so on up to what? kn minus 1 xn minus 1 x plus kn y, and that is what? An integer. So this gives d1 divides d2. Call this as equation number 2. Now here we have used equation 1. So you can write the reason here from 1. Okay. Or here also I can write using 1. I can write this. Fine. Using equation 1. Okay. Now one thing, d1 divides d2 we have shown. Now we have to show d2 divides d1. So for that, use this one. So now what can I take? This GCD of a1, a2, so on up to what? an, and that is equal to what? d1. Now by existence theorem we can write d1 equal to this addition of linear combination of this one with some integers. So therefore by existence theorem, what we get? Suppose a1 y1, plus a2 y2 plus so on up to what? an yn equal to what? d1. for y1, y2 and so on up to yn are what? Integers, belongs to z. Now here what we should do, we have to show d2 divides d1. So this side we have to show in terms of d2. So for that I must substitute a1 is equal to this, a2 is what? This one. Then an is what? Here an we get this one, d2 kn dash as such. So what we get here, a1 is equal to what? a1 is d2 k1 dash into y1 plus again d2 k2 dash into y2 plus so on up to what? an is what? d2 kn dash yn is equal to what? d1. So now we take d2 common, d2 will be common, k1 dash y1 plus k2 dash y2 plus so on up to what? kn dash yn equal to what? d1. This is again an integer. So this step shows what? d2 divides d1. Call it as equation number 3. So from 2 and 3 I get, from 2 and 3 I get d1 equal to what? d2. As they are GCD, both are positive. Actually we get d1 equal to plus minus d2, but it won't be negative, so d1 equal to d2, and d1 equal to d2 is same as to say our required thing. That is the GCD of a1, a2 so on up to what? an is same as the GCD of a1, a2 so on up to what? an minus 1 and an. These are what? Equal. These are equal. So this is about the general proof for this node. Now let me take the next example. Next example is that prove that A divides BC if and only if A upon GCD of AB divides C. This is the part. So now both way implication is this. So solution of this one, given that A divides BC. So A divides BC, so that gives BC is equal to what? AK1. Call it as equation number 1, or yes, this is equation number 1, and later on let me write for k1 belongs to what? Some integer. Fine. Now suppose the GCD of A and B is equal to what? D. Therefore by existence theorem ax plus by is equal to what? D. For some xy belongs to what? Z. For some xy belongs to Z. So this gives acx plus bcy is equal to what? dc. This can be written as such. Now this is same as to say acx plus ak1y equal to dc. Why? Because bc is equal to what? ak1 from 1. Fine. Now this gives a into cx plus k1y is equal to what? dc. Now this is same as to say a upon GCD of AB into Cx plus K1y. We know GCD is non-zero, so GCD of AB can be divided to both sides, D upon or DC upon GCD of AB. But the GCD of AB is what? D. GCD of AB is D. So if I substitute D here, D get cancelled as it is non-zero. So this gives A upon GCD of AB into Cx plus K1y is equal to what? C. So C is some multiple of A upon GCD of AB. So I get A upon GCD of AB divides C. So we have assumed this part and we have proved this part. Now conversely means what? Converse part we have to assume this. That is A upon GCD of AB divides C, that is same as A upon D divides C. So A upon D divides C, that is C is equal to A upon D into K, for K belongs to what? Z. For K belongs to Z. So now let us multiply by B here. So BC is equal to B into what? A upon D into K, or it can be written as A into BK upon D. B is also an integer. So BC can be written as some multiple of A. So this is same as, fine, this gives A divides what? BC. A divides BC. So this is our proof here. Now first time we have assumed this A divides BC and we have proved A upon GCD of AB divides C. Later on we have assumed A upon GCD of AB divides C, we have proved A divides BC. This is the proof here. Now let's go for the next part, that are the definitions of prime and composite integers. So the prime and composite integers, what are they? So, this is our new topic, prime and composite integers. Already we have learned these things previously also. Now here we have to learn some properties of them in detail, because number theory is the course of, mostly here the properties of natural numbers are there and prime numbers are also what? Natural numbers. So definition, let me take an integer p greater than 1, strictly greater than 1, is said to be, already I explained you that 1 is not a prime number, as 1 has only one divisor, that is 1, and a prime has two divisors, that is 1 and the number itself. Such a number is known as a prime divisor. So now here another type of example, definition I want to write. It is in another language, we can say. So is said to be a prime, is said to be a prime if it has no proper divisors. It don't have a proper divisors, then it is known as a prime number. Now again, an integer n greater than 1 is said to be composite. Is said to be what? Composite. If it has what? Proper divisors. If it has a proper divisors. Proper divisors means the divisors other than the 1 and the number itself. Proper divisors. Already we have written those things. So example, I can say 2, 3, 5, 7, 11, 13 and so on are what? Primes. Are primes. While 4, 6, 8, 9, 10 and so on are what? Composite. Are composite. Fine. Now let us take some notes. So note 1, suppose if P and Q be any prime, P and Q be any prime, such that P divides Q. P and Q are prime and P divides Q. Then it is not possible for prime. P must equal to what? Q. The number itself can divide to that if it is prime, because it has a divisor, the one and the number itself. So they must be equal. The second note is that for any integers A, if P doesn't divide A where P is prime. For any integer A, if P is not a divisor of A, then the GCD of P and A should be what? 1. For example, here I can say, for example, now suppose A is equal to suppose 4, yes, and P is equal to suppose 3. We know P doesn't divide or 3 doesn't divide 4. So this gives the GCD of 3 and 4 is what? 1. Such a various examples we can write. Now here I want to take one example which you are already familiar with that example. Still we should take it here. Suppose P is a prime number, then square root P is what? An irrational number. So let us take that example. Later on we will go for the next properties. So now example, for any prime P, show that square root P is an irrational number. Square root P is an irrational number. So solution of this one, let P is prime and suppose on a contrary, you know we had proved it with the help of contradiction. Suppose that square root P is a rational number. Fine. Now if it is a rational number, therefore there exists A, B are integers such that square root P is equal to what? A upon B, and this, you know, we are right reduced form of the rational number. So the GCD of A and B should be what? 1. Now if square root P is equal to A by B, therefore P is equal to what? A square upon B square. Fine. This is same as to say PB square is equal to what? A square. That is P divides A square. So if P divides A square, therefore P must divide A also. Fine. Now as we get P divides A implies there exists some integer in Z such that, or integer such that A is equal to what? P into K. Fine. Therefore this equation PB square is equal to A square becomes, let me substitute this value of A here. So that will become PB square is equal to A square is here. So A square is P square, K square, P square, K square. So now P is non-zero. So it get cancelled. As P is a prime, you know, it is strictly greater than 1. So it get cancelled. So we get B square is equal to what? PK square. So now B square is equal to PK square, that is same as P divides B square. Now P divides B square means P divides B. So now what we get here? While we assume P root P, square root P is what? A upon B. So we get P divides A, and when P divides A we get P divides B also. So here as P divides A and P divides B, that is 1 less equal, P is a common factor of what? A and B, and obviously P is greater than 1. So this contradicts to the fact. What does here? The GCD of A and B is what? 1. But here it shows P is greater than 1. So GCD of A and B will become P. That is 1 less equal P less equal what? GCD of A and B. Less equal GCD of A and B. So that is P is common factor. P is common factor of A, B, which contradicts with what? GCD of A and B is what? 1. Therefore, our assumption should be wrong. So, square root P should be an irrational number. Therefore, square root P is an irrational number. Square root P is an irrational number. Now, in next part, we have to take some properties of prime numbers. So, we will stop here. We will take them in next video. Thank you.